time during lecture, so I said I'd post a short video on the two remaining topics. So let's do experimental design first, and then we'll do significance tests. So for experimental design, the basic thing you should look at, the first thing you should ask yourself, is it a randomized study? So is there a randomized experiment, or is it a non-randomized experiment or observational? Both of these you can lump together. Observational and non-randomized experiments. The key is the randomization is key, because what it allows you to do here is it allows you to conclude, it allows you to meet the goal of having the treatment and the control group as alike as possible. And then when you administer the treatment, that's the only difference between them. So at the end, when you look at the results, you can say, since they're alike in every way except for the treatment, you can conclude causation. So that means there's no systematic differences, which is no confounders. So you can conclude causation. If you see a difference at the end of the study, because randomization breaks all the systematic differences. Now, if you have a small sample, you might have some accidental differences. So you can block to get rid of accidental differences in small samples. But final assignment to treatment and control has to be random. Okay, and then you've got a good study. So the only kind of blocking or stratifying into groups, where you decide what might be important, happens before the randomization. Okay? After randomization, compare. You have to keep everybody who was originally assigned to the two groups in their, you compare everyone to everyone. So you compare always everyone in the treatment group to everyone in control. So you want to include people who drop out of the study. So if it starts off randomized, you can do some blocking to begin with, then you can randomize. But after you randomize, you have to keep that randomization. You don't want to break it. Otherwise, you're going to introduce bias where you didn't have any to begin with. Because people are going to, you don't want to break the randomization. So that's the idea there. And then with the observational, they start off different to begin with. So they start off different. They choose themselves into these two groups. So there's always confounders. They have confounders because there's systematic differences between the two groups. So they're bound to be different in lots of ways. And the problem is, you don't know what's causing what. You don't know if the treatment is causing a response. It might. Then you could think of what could fit in that box going in that direction. Treatment causes something that causes the response. Or you have this other situation where you have a confounder in here that's causing both the response and the treatment. So basically, these two look associated just because you have this third variable that's causing both of them. But you don't want to, if you got rid of the treatment, it wouldn't make any difference. This one's still causing the response. Okay, so the idea is you've got these confounders that are messing things up, and you're comparing apples to oranges. The treatment and control are not alike because they chose themselves, so you can't tell if the differences between them are what's causing the response or the treatment's causing the response. So what do? So then, at the end of the study, well, you can't do anything before they've chose themselves, or fate, So then, after you look at the responses, what do you want to do? You want to compare apples to apples, so you break them into subgroups. So you break the population into subgroups, along the confounding factor. So you want that confounding factor to be the same. If you think gender is confounding something, you would compare males in treatment to males in control, right? Because then you're comparing males to males. It's separating out. So males, it's not the fact, do the same with the females. That way the confounder gets eliminated. Then you can move on to other confounders. So this is stratification, and it happens at the end of the study. To make groups more alike. Okay? Whereas the only time you're going to divide up into groups is this blocking, and that's at the very start before you do the randomization. Okay, so that's the idea. And here, you can conclude causation, and here, all you can say is there's an association. There might association between the treatment and the response, but you don't know if the treatment's causing the response. So association or correlation, not causation. Okay? And here, that's the key thing, you can conclude causation. Okay, so that's basically what you should be looking at for the experimental design. And now, we said we'd move on to just look at these significance tests. So after, let's say you have this randomized study, and then afterwards you see some difference, how big a difference do you have to see before you can say that, hey, it was the treatment worked. It wasn't due to chance. So, because there's bound to be some differences just because the two groups have different people, just due to chance variation. So we're trying to, with these significance tests, we're trying to separate out what's due to chance variation and what might be due to an actual cause. Is it two? All right? So the way that we do these is we have this null hypothesis. You know that part. You assume that the difference you see is just small and due to the luck of the draw. And then you add an alternative that says, no, the difference is too big to be due to the luck of the draw, right? And then we have these test statistics that we looked at. And we already talked about the Z a lot. And basically the Z statistic is what? You have this observed minus the expected, some kind of difference between what you observe and what you'd expect under the null. And then you divide it by your typical sampling error. So what you're looking at is some kind of sampling distribution of this test statistic. And the Z statistic, it looks like the normal curve here. And so when the null is true, this is the distribution of your sampling statistics. This is, you have some null box that this is based on. The expected is based on the null. And, each time you take a sample, it's going to vary. So this is the distribution of that. And then you say, okay, you expect around here, but if it gets too weird, your results your observed is too far from your expected way out here, the probability of that P is so low, you're going to reject that null. So that's the idea. So you reject the null if your statistic is too big, past some point, all right? And then you say, we reject the null, we don't think it was due to chance, right? And then the next, so this is the basic, all our statistics are of that form. The Z and the t look very, very similar. This one just has still the observed minus the expected, but this one has a standard error that's tweaked a little bit. You divide basically the standard deviation by the square root of n minus 1 by its degrees of freedom is n minus 1. And you have these t curves. If this is the z, you've got these t curves that are fatter in the tails. So let me draw it. So if it's fatter in the tails and less in the middle, I'm doing an exaggerated version, you're going to have these fatter tails, so your p-value is going to be bigger for the same test. So you're going to get this bigger. In other words, you need to go further out to reject the null, more evidence to reject the null. Okay, so what else do we need? Okay, so that's the z and the t. And so this has fatter tails. So it's going to have a bigger p. We like small p's because then we can reject the null. This is going to have a bigger p, so it's going to be harder to get significance because that's the area of the tail. Area of tail. All right, so that's the basic. Those are two statistics, and you have to know those. We're not going to be giving them to you. All right, what's the next ones are, this is for one sample. What if you have two samples? Well, here you're, okay, so then you're going to have the two sample ones are going to be what? You have some difference between two samples. So that's the observed difference between like the means or the percent, something between it, minus your expected under the null. And that is always that they're the same. So that's 0, no difference. That's your null. Over the standard error for the difference. Now we're having two sources of variation from the two samples. So what is this? This is combining the two standard errors by the Pythagorean theorem, basically. So you have the standard error of the difference between the two sample averages. It's going to change all the time, and it depends on what? Well, it's the square root of the sum of their squares. It depends on the size of each of them from, let's say, sample A and sample B, and you add them together. Okay, so it's going, this, you know, it would look like that. That's the standard error from one of them. That's the standard error from the other. And this will be the standard error of the difference. So it's bigger. The standard, of course, this a squared plus b squared equals c squared. This is longer, bigger than either one of these, but smaller than the sum. All right, so you do an equivalent one with the t, but you know, just have the standard error plus of the difference, and then we move on to these statistics that look a little bit different. Those are the chi-squared. And let's see, the chi-square statistic is going to be given to you on the exam. It will be on the last page along with the table. You'll just, what will you see? You'll just see, what is it? It's the sum of the observed minus the expected. You're seeing that divided by the expected. So, but then this top part, the observed, you have a bunch of different categories. You can't boil it down to a single number. You have a bunch of them. So you can't just, some of them are going to be positive and some will be negative, and they could, you know, cancel each other out. So you have to square them. In fact, the observed minus the expected will always sum to 0. So you have to square them to get the size of the difference. It's still the same thing. How far your sample, your observed sample, landed from what you'd expected under a null. It's still that. It's just since you're combining a whole pattern of differences, you square them. Because you can't boil it down to a single number like you can here, a single sign number. The z and the t can be either positive or negative, depending on if it's this direction or that direction. Right? The p-value can be on this side or that side. But this, chi-squared, is always positive. It's squared, and it's because you're combining a bunch of differences, multiple categories. Okay, so that's the deal there. And we use it, we learned two. One was when you have one variable with multiple categories, and the other And that's, what's that called? Chi-square goodness of fit. That's what this is called. They use the same statistic, but this is the goodness of fit one. How well does it fit a particular model? Okay, how well does it fit some model? So one variable, this is the chi-square goodness of fit here. The null is a model, and you're wondering how well your observed data fits that model. Your one variable has multiple categories, basically two or more, multiple categories, and they're counts. They're not it's a count, whether how many are in each category. Okay, and it's a chi-square distribution, and the degrees of freedom are equal to the number of categories minus 1. All right, so that's that. And it's always positive. So it's only right-tailed here, and something like that. Okay, it's only, this is 0. Can't be negative. All right, now what's the other one? The other one is this is the chi-squared goodness of fit. This is the statistic for both of them, and you're going to be given, that's the only thing you're given. And then there's this chi-squared independence test. And what's that? The chi-square independence test is, sorry, that little thing. All right, the chi-square independence test has two variables, and the null is they're independent of each other. So basically, like if you had two variables each with and the null is that they have the same proportion of within each one, the categories, the distribution among the categories is the same. So they're independent, two variables. So what do we have then? So we have two variables, each with multiple categories. Okay, and then what do we have? The degrees of freedom. How are you going to remember it? Well, it's the same thing, but now you have two of them. So you have the number of categories for variable, for one of the ones, for variable 1 minus 1. That, what do you do with that? Times the number of categories for variable 2 minus 1. Okay, so it's just this for one variable times for the other variable. Okay, so what's your test going to look like? So you'll be given the observed, right? And you're going to have to find the expected. So I strongly just recommend that you look at the examples and know how to figure out the expected for each of them. All right, I think that's. If you do the practice exams, you'll see that. If you do the study guide, you'll see that. So is there anything else? I think that's it. I think we covered everything else. Look for the in class today. Okay, so good luck on the exam tomorrow. Bye-bye. Or today. You're going to be watching this the day of the exam, I guess, because by the time it's posted, it will be early morning. Bye-bye.